Alright, lesson 122, they're going to get into a lot of pumps and motors and all kind of things. So the beginning of the EWR talks a lot about well pumps, jet pumps, things like that. I'm not too worried about that stuff. I'm more worried about where the chapter gets to motor circuit design and onward. This is kind of the really important stuff, and this is kind of a big idea. There's a lot of code references and articles that I'm going to reference here. So really make sure you take the time to find those in the code book. Look at them yourself and spend a moment beyond sort of this PowerPoint in this video to get to know those code sections. So first thing we want to do, if a customer calls, hey, I've got a new piece of equipment, a motor that needs hooked up, you as the electrician, obviously you're going to have to run conduit to begin with, full wire. You're going to need to install a breaker, disconnect with fuses. And so we need to know how to size that stuff. Many times an engineer does it on a set of plans, but sometimes you're working direct for a customer, and it's up to you to know how to size your wire, your breakers, your overcurrent devices, things like that. And particularly with motors, there's some intricacies that should be pointed out. So right off the bat, I'm going to look at a motor nameplate. They're all a little different, but they all contain some very similar info. So, and there's a lot of this on here we don't care about, but particularly we need to know horsepower. This one's 50. This is a dual rated motor, so this one could be operated, and these are all ranges. So again, we're going to operate probably at 208 or 240, but the range for the low voltage range is marked as 230. Same with the high voltage range of 460. Again, we would operate that at 480. But for calculation purposes, it's listed as a 230/460 motor, so keep that in mind. This one is a three-phase motor. We treat single-phase motors just a little different, but it's really not a big deal, and I'll try to highlight what the differences are. And then here's the amperage. They give us two different amperages. Reason being, it depends which one of these voltages we are hooked up at. So motors, unlike resistive loads, we know on resistive loads if we increase the voltage, we also increase the amperage and wattage. Not the case on a motor load. It's actually the exact opposite. So if voltage is lower, amperage is higher. When voltage is higher, amperage gets lower. These things kind of balance out to sort of equalize at this 50 horsepower, so that motor is going to run where it needs to. And then the last thing I want to point out is these connection diagrams. So this particular motor is going to have 12 leads. If we're going to run it at this lower voltage, we're going to connect everything like this. If we're going to run it at the higher voltage, we'll connect up like that. So I'll pull some of these values here that we're going to use. Let's use the values off this nameplate and start calculating some circuit sizes and things like that. So the first thing we need to find is actually what's called the full load current, or the full load amperage. So first table we want to reference 430.248. This is for finding full load current for a single phase motor. Okay, and now in this case I did say we're using a three phase. So if we're going to do a three-phase motor, we're going to flip the page to 430.250. Either way, these tables work the same way. You just need to make sure you're in the right one for the phase of motor we're working with. So in this case, we do have a three-phase motor, like I said, so we are going to use 430.250. We have a 460 volt motor, so you can see we have a column for 460. And in this case, it's a 50 horsepower motor, so we have a row for 50. So all we do is find out where these two intersect. So our full load current, or our full load amperage, is going to be 65 amps, okay? So we'll pull that over here. Notice it's slightly different than the nameplate amperage. This nameplate amperage is used for sizing overloads, which is something maybe we'll get into in the future. But for now, we need the full load current, sometimes known as full load amperage. Same thing either way. So once we have the full load amperage, the next thing I like to do is we're going to find our overcurrent protection size. Okay, so we have another table, 430.52. It's used for sizing our overcurrent protection, and these numbers here represent a percentage of the full load current. Okay, so our full load current we know is 65. Depending what we use, we're going to multiply it by whatever the particular percentage is. 99% of the time you're dealing with dual element time delay fuses or inverse time breakers. So non-time delay fuse means as soon as it's a 100 amp fuse and it gets to 101 amps, it blows immediately. Dual element time delay fuse means it's going to be okay with a slight overcurrent for a little while. It'll put up with that. Instantaneous trip, again, as the name implies, as soon as you have any overcurrent, we trip. Inverse time means essentially the higher the overcurrent, the lower the amount of time it takes to trip, and vice versa. But 9 times out of 10, or even 99 times out of 100, you're using a dual element time delay or inverse time. Again, we're only talking about single phase and AC polyphase. Poly meaning many or three phases. So really you're only looking sort of at most times these four different options, or two options really. And in this case, let's just go ahead and say we're going to use a dual element time delay fuse in this case. So what we're going to do, we're going to take our full load current of 65 times the percentage we found here, which is 175%. So that's going to give us our amperage of our minimum amperage of our overcurrent protection device. In this case, our dual element time delay fuses. So let's go ahead and mark that down here. Now, I think it's pretty obvious you're not going to find a 113 amp fuse. So we do have to add one more code section here, and that's Article 240.6, which tells us our standard amp ratings of overcurrent protection devices. So I'm going to come in this list and find the next one bigger than what I need here, right? So I can come in here and see 125 fits the bill. So I'm actually going to install some 125 amp fuses in this case. So now we've got our overcurrent protection size. Let's start sizing some wire here. So the textbook's going to tell you, and the code will tell you as you guys read, our wire is based on our full load current times 125%. Why do we do that? Well, the short answer is basically a motor could be a continuous load. If you recall, all continuous loads, our conductors must be sized to 125% of the load. Okay. So we're going to go ahead and do that. 65 amps full load current times 125%. We get 81.25 amps. So I need wire that can handle 81.25 amps of current. In this case, and unless you're told otherwise, let's just go ahead and assume we're using copper THHN. If you recall, I think we were in this section prior. Sort of your rule of thumb, if you're just trying to say, hey, I need a wire that can handle this many amps, you're going to go right to the 75-degree column. If you remember, we got to use sort of the weakest link in the chain theory. So every element of your circuit would have to be rated 90 degrees. Your terminals, your splices, anything, the wire itself. And 99% of the time, probably 100% of the time, not everything's rated 90. But it's a very safe bet, and for our classroom purposes, we can assume things can be rated 75. So anyway, we're going to go right to the 75-degree column here for copper wire. We need a wire that can handle 81.25 amps. So we scroll the list here, we get down to this one that can handle 85. And we're going to see that that actually is a number 4. So we're going to pull number 4 wires for our conductors here. Okay. So that's essentially our current carrying conductors, right? We have another conductor we have to size, and that's our grounding conductor. And I don't think we've been to this particular table before, table 250.122. I think I mentioned, maybe, I don't expect you to remember the code, but there's a few tables I highly suggest you do. The first being 310.15b16 back here that we already looked at. But then the next one, really important one, is 250.122. It tells us minimum size equipment grounding conductor. And in this case, it's based on the rating of the overcurrent protection device. Okay, in this case, we already found out it's 125 amps. So we'll come down here, so it's not exceeding. So if we've exceeded 100, so we got to go to the next one, which is 200. We're pulling copper wire, so we're going to go ahead and pull a number 6, just like they show here. Okay, so at this point we've got our fuses, we've got our wire. Really only one thing left for it, the size, and that of course is our conduit size. So this is a new topic, I think, that we haven't covered. So pay attention closely because it's a very important topic. Okay. So to size a raceway, okay, first thing I'm going to do is go to chapter 9, table 5. So all the way in the back of your code book, chapter 9, table 5. And notice this is about the second or third page, because every single individual type of installation has its own size associated with it. So make sure you're looking here of the right type of installation. Again, for example purposes, we're almost always going to use THHN. So that's going to put us down in this section with the THHN, right? So we know we have number 4. So we come down here, find number 4. We're looking for approximate area, okay, because we want to know kind of a cross section of the conduit. How much area are we going to fill up? So we're looking at approximate area in inches squared. You can do millimeters squared if you want. I'd say stick with inches squared if I were you. But so we're going to come down here and find a number 4 in inches squared has 0.0824 square inches of space required, right? Another item here to mention is So I take this square inches times 3. I'm doing that because we're going to have 3 wires because it's a 3-phase motor. Okay, so a single phase motor, you're going to have to run 2 wires plus a ground. 3-phase, we got to run 3 wires plus a ground. So I'm multiplying the square inches of 1 number 4 times 3 because I have 3 wires. So of course you do that, you get 0.2472 square inches. We have to account for our ground as well, which we said is a number 6. So 1 number 6 takes up 0.0507. Of course we only have 1 ground, so we multiply by 1. And then let's go ahead and just add these two values together. We'll get our total square inches of space we're going to need to fit inside that conduit. So we need a conduit that can contain 0.2979 square inches of wire. Okay. So the next thing we're going to do, we're actually going to flip to the table just before table 5, and that's table 4. Again, table 4 is several pages long. For every type of raceway, there's its own little section like this. So again, take some time to turn to the table, get familiar, but please note that you got to check the right type of raceway and make sure you're checking that particular table section. So the other thing to note here is we have these different headers. We're pulling over 2 wires, so we can only fill by code up to 40% of that conduit, which sounds odd, but if you really actually calculate this, you're going to see that gets pretty full pretty fast. But anytime you're pulling more than 2 wires, we're looking in this column right here, and that's almost every time, right? So we need to find which one of these square inch values can contain our 0.2979 inches, and we go down the table here and look, and we see that we actually get to this particular size here, and that's a trade size 1 inch. That tells me I need to run a 1 inch conduit. Okay, so you know, if we think about this, we kind of figured everything out backwards as to how we're going to do it. We would actually run the conduit first, then we can pull the wire, then we can put the overcurrent device in, and then hook everything up. So it's kind of neat, sort of the back and forth you got to think about. But you can see that was kind of a long list of things we had to do, and don't fret here because again that was a lot. I did put a link on the LMS for a little worksheet that I created, which is kind of a brief step-by-step. It's intended for, you know, apprentices and people in the field can actually sort of fill that in if they were to actually have to do this. So that is available on the LMS, so please check that out as well. Again, it's kind of a brief version of this. It walks you through, kind of has everything in writing with the table references and everything. But again, make sure you actually look at these tables for yourself, because I just got snippets of the table. Many of these tables are several pages long, so become familiar, make a mental note of where they are, and because throughout this chapter in your career you're going to be going back and forth to most of these tables plenty of times. So anyway, like I said, spend some time, get to know it.